Okay, welcome back. Lots to cover in this video, as you can see by the title alone, but please hang with me because really everything else we'll do in this course will build on or directly tie to what we talk about in this particular video. So yeah, hang in there. Today we'll talk about hypothesis testing, p-values, power, and effect size, really the backbone for hypothesis testing, which is what we'll do the rest of the course. So last time we talked about estimation and confidence intervals. I don't want to spend a lot of time on this because, like I said, lots to cover. But if you'd like to compare the two, you're welcome to do so here. But the key difference really comes down to this bottom row here, and that with estimation, we weren't making a decision, right? We're just estimating values, estimating parameters, and in hypothesis testing, we are making decisions, right? And so today we'll walk through sort of what that process looks like and what types of decisions we're making. And so if I ask you this question, what is a hypothesis? This is something that I imagine you might have come across before in science classes. Like for me, I remember in like fifth grade science having this conversation. And so our exposure to it varies. But nonetheless, no matter where you're at, let's do a quick little refresher here. So a hypothesis, generally some sort of testable statement, explanation, or prediction. So, for example, my own hypothesis is that envy apples are the best apples. Come at me, come on, fight me, because I will die on this hill. I don't know why I love this so much. I'm filming this in my office, and I literally have one right on my desk in front of me. I just restocked it in the store today. But I do love envy apples. However, this is not a very good hypothesis, right? This is really just a matter of opinion, and it's like, okay, best apples according to whom, right? There's a lot of details we need here to really punch this up. So maybe I'd say, okay, fine, envy apples are the most popular apples. But again, the same argument stands, according to whom, right? Who says they're the most popular and compared to what? Compared to what other apples? What is it compared to Granny Smith, right? If Granny Smith is your go-to, then I'll drop you from my course because I won't actually do that. But I just fundamentally disagree with you. So maybe we want to punch it up even more. Like I remember being taught hypotheses were if-then statements. So you might say, okay, if people blind taste test one apple from each of the apple varieties at Fred Meyer's here in Fairbanks, then they will most often rank envy apples as the best. Right. So you get my point, right? Like we need to provide more information for these to be truly testable or as precise as possible for whatever our study might be. You might also say, okay, it's not an if-then statement. Maybe we'll say it's some kind of effect, like eating envy apples during statistic lessons, like this one, will make the experience more enjoyable. I would agree. I would love to be eating one right now, but that would probably be quite distracting for you. Right, and so it's just a quick refresher, and hopefully, I don't know if that was funny or not, but I thought it was, and so hopefully that'll at least help me make a better video for you. So purpose and goal here. Basically, here we're looking at, all right, I guess backing up, hypothesis testing is always a little bit, I think, counterintuitive when you really get into the weeds, because I think most of the time we think that we're just focused on the sample statistics. Like if I collect a sample and I calculate a mean, right, I'm just focused on the data from the sample, and that's true, but we're also comparing it to hypothetical population parameters, right? Because again, like we've talked about in previous videos with sampling distributions and whatnot, ultimately we're always kind of thinking of those things in the background, or even if we're not actively thinking about it, the theory of statistics was built on this premise of estimating population parameters from sample parameters. And so here we're generally focused on the mean in these examples, and that's most of the analyses that we'll do in this course come back to the mean or focus on the mean. And so there are different ways we'll do that, but generally speaking, 4 steps to each of those processes. And so the first step is stating the null and alternative hypotheses. Second is setting a criteria for a decision, or technically a criterion. The third step is computing the test statistic, right? It could be a Z, a T, an F, right? Whatever it may be. And then the fourth is making a decision. And so we'll walk through each of these first, starting with step 1. So let's define null and alternative. Null hypothesis, or H sub 0, H naught. I tend to say H sub 0, or just H0. So the null hypothesis, this is some statement about a population parameter, because again, we're thinking about population parameters and hypothesis tests. So generally, we'll be doing this about the mean, and we're making some statement that we assume is true about that population parameter, right? And null, generally, you can think of meaning like no effect or no relationship, right? Null just means nothing's really happening. And so this could just say that these two things aren't related, or it could be a rough starting point for comparison. So we might make some assumption about the population mean mu here, right? Like we've used IQ tests as an example in here. IQ tests are an easy example because the population mean for IQ tests, the way they're designed, the population mean is supposed to be right at 100, right? So we can make that assumption as a null hypothesis. The alternative hypothesis, then, that's where things get fun and juicy, right? Some sort of statement that contradicts the null hypothesis, right? So um, could be some statement about the expected effect or expected relationship, right? If we say these two things aren't related in the null, in the alternative, we're saying that they are. So this is really like where I'd say our predictions lie. We just need the null hypothesis as part of the formal steps in this logic, this I guess logical testing process that we're following here. Um, and so in our alternative, we can do a couple things. We could predict that basically these two things aren't equal, right? Like for example, our population mean does not equal the sample mean, or vice versa, rather. We could say that one is greater than the other, one is less than the other, right? And so generally, we're comparing like if we're thinking about the mean, we're typically in the null hypothesis talking about the population mean, and then the alternative hypothesis talking about the sample mean, right? Or using our sample mean to inform another prediction about the population mean that contradicts that which we stated in the null hypothesis. And so some examples here to give a little bit more context. So say, for example, we just wanted some rough estimate of a population mean. So it could say children in the United States watch 3 hours of TV per week, right? This, where's my mouse? There it is. We could say that's our rough estimate of a population mean. I think it's today way more than that, sadly. Um, but that would be an example. An alternative would be, okay, children do not watch 3 hours of TV per week, right? And you'll notice here that we're not saying it's more or less, we're just saying it's not equal. And so that's an example of that not equal. So here we're saying H1 is not equal to H naught. In other words, the population mean stated here is different than the population mean stated here. We could say that we could just go more than, right? So in this case, we're saying H1 is greater than H0. In this case, we're saying less than. H1 is less than H0, right? So point is, right, in these we had the exact same null hypothesis, but three different ways of expressing an alternative hypothesis. But again, the common theme is that these are contradicting that which we stated in the null, right? So again, it feels a little awkward, I think, when you first start doing this, but generally it's just a way to more explicitly put our logic onto paper as we go through this process. And so moving on to the second step, setting the criteria. Well, as you think about this, I'd like you to think about, imagine if you're going into surgery. It's hypothetical. Which would you prefer? Would you prefer a doctor coming in and saying, hey, I've done the surgery a lot, I know what I'm doing, but all things considered, it's out of my hands, and there is still there's a great chance of survival, right? There's a greater than 95% chance of survival. Or would you rather they say that than say there's less than a 5% chance of death, right? So, yeah, greater than 95% chance you're going to get up and walk out of here, you'll be fine. Or less than 5% chance that you're just going to die on my table and I'll keep on living, but you'll be dead, right? I don't know what you'd prefer. Personally, I'd prefer the chance of survival because that's just a little bit more positive, and I think to me it feels a little better than just thinking about any chance of death here. Especially when you have no control over the situation, right? You'll be knocked out. But ironically, or perhaps ironically, we kind of frame things in this death way in hypothesis testing. Not to say that we're talking about life and death scenarios, hopefully, at least not in my line of work. Um, but we are focused on these less than 5% chance of failure, right? And so that's something I wanted to mention right off the bat before we get into this, because we're about to start talking about p-values, something you might not have exposure to, or even if you do, I think we're often taught these incorrectly. I didn't really get taught these well until I was like a grad student. Um, and so in step two, we're talking about setting a criteria for a decision, right? The decision we'll make in our hypothesis testing process. And in setting the criteria, we're essentially stating a level of significance. And so this gets wordy, a criterion of judgment upon which a decision is made regarding the values stated in a null hypothesis. Um, I'll give a practical example here on the next slide to make this much easier to digest. But we also refer to this as alpha. Alpha is the level of significance. Typically in behavioral research and social science research, we talk about an alpha of 0.05, or that's kind of the borderline cutoff where if if yeah, so alpha is essentially our level of significance, and it's usually reflected in our data as p-values, right? That's the actual number we report or the statistic we report and interpret. If we have a p of 0.06, for example, typically we would reject that, right? We would say, okay, that is an insignificant finding. But if we find a p-value less than 0.05, then we'd say, okay, this is a significant finding. There is some sort of effect there. Right, so that's kind of just the borderline cutoff we often see. And again, we'll go through this plenty of times. I promise it'll make sense. Yeah, so typically reported as p-values. You can see some examples here. But let's do a practical example to explain what these are and how we interpret them. So this is a weird example. However, it was the simplest one I could come up with. So please bear with me and have an open mind and know that I am a heteronormative male, and so I'll be talking about this from that perspective. So let's say I've got a crush on someone, right? I can remember some of my first crushes when I was a young boy back in grade school, right? I had crushes on people, and so let's say I've got a crush on someone, right? Except in this example, I guess I didn't have a phone until I was like 16, so we'll say I'm 16, right? I'm a high school student, got a crush on someone in class, and I crush on them. Oh, I crush on them secretly. And then one day I get a message from them, right? And so in this case, we'll refer to that as my sample, right? I get a message from my crush, and it seems like they're into me. I don't actually think through the content of what they said. I don't know. Maybe they ask if I can hang out with them over the weekend, right? And so I'm just like, oh shit, right? I'm so like, I want to say in love, but that's too much. I'm so infatuated by this person. Clearly, I haven't done this in a long time. High school was a while ago. But I get this message. I'm all excited and just like, yeah, I'm overcome with emotion. And so, me being the anxious person that I am, I start overthinking this and immediately compare it to like every message I've ever received. Right? Being an astute scientist and an overthinker, I'm maybe not actually going through every message in my phone, but I'm just kind of going through that, doing that little like mental, emotional math. Right? I'm just like, oh my god, what does this mean? Do they actually like me? Yada yada yada. So that's my population, right? All the other experiences and whatnot that I might have. And so with that in mind, then I'm thinking about this. I'm kind of spinning my wheels, and so I asked some friends for help. Right? I asked them for their predictions, which we'll use as analogies for null and alternative hypotheses. And so one friend is quite pessimistic, and well, I suppose it's a valuable friend to have. But they say, "Sorry, dude, she's just not into you." Right? There's no effect. There's no relationship there. That's like the null hypothesis, right? They're just saying there's nothing there, right? Like you're overeating it, or over what's the term? Over analyzing this, right? Like you're assuming too much. There's just nothing there, and so I don't like that answer. So I go and find another friend who's just like, "Whoa, dude, she's into you, right? Like there is some effect relationship. This is our alternative hypothesis, right? So now I have these two contradictory things, right? One saying there's nothing there, one saying there is. And so, in a basic sense, using our previous notation, we're saying that these two are not equal to each other, right? So it's like our null and alternative hypotheses. And so I have all this, and I'm still anxious, and so I'm sweating a little bit. And fortunately, in this hypothetical example, I can run an analysis using the magical love doctor stats machine. This is not a real thing, but it helps me with this analogy, so we're going to pretend it is, right? And so I ask it, I say, all right, magical love doctor stats machine TM, what is the probability that I would have obtained that message if she wasn't actually into me? In other words, if she wasn't actually into me, would I have ever gotten that message? Give me a number here, right? What's the probability? And this thing doesn't have great bedside manner, but it kicks out a result. And it says less than a 5% chance, P is less than 0.05, right? And so that is exactly what we're talking about when we talk about p-values, right? This example is weird, I'll give you that, but it is actually an accurate depiction of p-values. And I think that's something people often miss or misunderstand or misinterpret when we're teaching or learning about these. And so, in a more literal sense, what is the probability that I would have obtained that sample statistic if the null hypothesis were true? In this case, it just so happens that the sample statistic was that message, right? And the null hypothesis was that there's nothing there, right? She's just not that into you. Right, so hopefully that helps. We'll come back to this. That's kind of my brief way to explain these. And so that alpha then, in this case, that criterion, that 0.05, is based on the probability of obtaining a sample statistic if the values stated in the null hypothesis were true. Right, that's what we just walked through on the previous slides. So for example, if we're talking about mean sample means, when the probability of obtaining a sample mean is less than 5%, if the null were true, then we reject the null hypothesis, right? We haven't gotten to step 3 where we make these decisions, but our 2 decisions to preface those are to reject the null or retain the null, right? Or you can kind of flip that on its head and think we're accepting the alternative hypothesis or rejecting the alternative hypothesis, or basically accepting the alternative or accepting the null. And so to put this in other words, if the null hypothesis were true, we would accidentally obtain a statistically significant result less than 5% of the time if we're interpreting p less than 0.05. To take that even simpler, if there were actually no effect, our results would show no effect with 95% certainty. And inversely, if there actually were an effect, our results would show that effect with 95% certainty. Right? Kind of some different ways to interpret this or to think about this. Some start to get slightly less accurate, but I think the cost is worth the benefits here. The benefits being just understanding this. So going back to that example with my crush in high school, you could say, okay, I'm 95% confident that she wouldn't have sent that message to you if she wasn't into you. Right, and that's a double negative, so maybe that one doesn't stick as easily. So you could say, I am 95% confident that she would have to be into you to send that message. Right, this is kind of the logic. Yeah, like I remember being in high school, and that's the exact scenario, but when you talk to people, like there'd always be kind of this mental math that you're doing, right? And believe it or not, we're talking about probability statistics and maybe even p-values if we're using this kind of language. And so when we do these analyses, when we interpret p-values, what we're really doing is interpreting these distributions, right? And so typically it depends on the analysis, right? If we're looking at both sides of the distribution, a two-tailed analysis, or just one side, like in this case, it's a one-tailed test. But basically, we're drawing some line in that distribution, and we're seeing if our observed result, or our sample statistic, falls on one side or the other of that arbitrary line, right? And as we go through the test, we'll go into more technical details of that actual process, but for now, just know that that's what we're doing, right? Looking at distributions. And so in step 3, we're going to compute the test statistic, right? We've got our hypotheses, we set the criteria, let's compute the value. And this, we're not going to get into the technicalities here, but broadly speaking, these are what help us decide about the null hypothesis. Everything we've talked about so far. And broadly speaking, the larger the value of a test statistic, the further a sample mean deviates from the population mean stated in the null hypothesis. Right, so in other words, the larger the value of a test statistic, whether it's a z-score, a t-score, an f-score, whatever it may be, generally that means our sample mean is further away from the population mean than a smaller test statistic. Right, and so one way, we'll get to this very shortly, but we'll talk about effect size. This is just one way to visualize what we mean by this, right? And so as the value increases, in this case 0.2, 0.5, 0.8, you can see the distributions are getting further and further apart. And so to pull up a visualization, I won't spend too long on this. This is from a website, Our Psychologist. We've been here before. This is visualizing effect size, which we'll get to shortly in this video. But the reason I wanted to pull it up here is just to show you. When I drag this to the right, you can see this is our D score. It's also seen right here. When I drag it to the right, the D score increases. And you can see that these distributions are getting further and further apart. Right? And so in this case, it's a control and a treatment. So these are two different groups. Right? But that's literally essentially like what these statistics are doing, or what these tests are doing, is they're basically looking at this difference. Right? And the higher the value of our test statistic, the further apart these two are. Generally speaking, right? That's ultimately what's going on behind the scenes when we do this. So I'll give you that information in Canvas. I encourage you to play around with it. This slide is scary. Don't let it scare you, because we'll walk through it the rest of the semester. But basically, these are all the hypothesis tests we'll cover in this course. We'll also cover correlations, but those don't quite fall under this umbrella of tests for differences between groups. And we'll walk through that, but for now, just know that these are grouped into the different statistics that we'll calculate or compute, right? So in other words, as we go through the semester and do hypothesis testing, we'll follow these same 4 steps, but in step 3, when we compute the test statistic, this is what will change. Either we're calculating a Z statistic, a T statistic, or an F statistic, right? And the context might change in the specific type of test we're doing, but we're always going to be computing one of these three statistics. And so making that decision, that is based on the p-value, right? And the p-value is directly related to the test statistic, right? So as the test statistic is larger, generally the p-value will decrease. And so p, again, representing the probability of obtaining a sample statistic, given that the value stated in the null is true. And so our two decisions here, the first is to reject the null hypothesis, or the two possible outcomes of our decision. Right, we might do this, we might reject the null hypothesis if the sample statistic is associated with a low probability of occurrence if the null is true. And again, we'll kind of walk through some examples here. So test results are statistically significant when p is less than or equal to 0.05. That's generally our cutoff. And really it depends, it really just depends on what criterion you decide on, what your alpha level is. But like I said, in social science research, almost all the time we'll look at p less than 0.05. In fact, the only time it would change is if we're looking at a lower p-value, like 0.01 or 0.001. And then if our results are not statistically significant, if we get a p-value that's greater than 0.05, generally we retain the null hypothesis. And so this means that the sample statistic is associated with a high probability of occurrence when the null is true. And so to go back to my story, right, or my example with my crush, to refresh you on our hypotheses, the null hypothesis was saying that there's no effect, she's not into me. The alternative saying that there is an effect, right, she is into me. Then we can kind of make 4 different possible decisions here. There can be 4 outcomes to our decision. Right, for starters, we can retain, there's a lot on the slide, so just bear with me. We can retain or reject the null. In fact, can I make, yeah, I'm gonna make this a laser pointer. I don't know if this helps or not, but so here, I can retain the null or I can reject the null. If I'm going to retain the null, right, that means that I'm going to say, okay, I guess she's just not into me, right? I'm going to retain the null hypothesis, and I'm going to side with this friend and say, okay, you're right. Yeah, there's nothing there. I was reading too far into this. That's one possible decision. Another possible decision is to reject the null. Say, no way, she's definitely into me. I'm going to ask her if she wants to hang out. Maybe I can tell her how I feel, ask if she wants to go out on a date, right? Whatever it may be. Just kind of communicate my feelings there. All right, so that's another outcome, right? Retain the null, reject the null. She's not into me, she is into me. And I am a human being, so I can be right or I can be wrong, right? And so the truth about the null hypothesis, right? That's what's actually real. So in this context, it's her actual feelings. Either it's true, the null hypothesis is true, and she's not into me, or it's false, and she is into me, right? And so I can be correct, right? So a true negative is when I retain the null, and that's actually true, right? So turns out she's not into me. She's just a nice person. She wants to hang out as friends. That happens, right? And you should still say yes, right? It's good to have friends. And if I retain that, I say, okay, I guess she's not into me, then that's a correct decision. That's what we call a true negative, right? A true positive then down here is correctly rejecting the null and saying, no way, she's definitely into me, and that actually being a reflection of reality, right? If she is into me and I say, okay, I think there's something there, and we talk about it, bam, true positive, correct decision, life is good. However, I can be wrong in either circumstance too, right? For one, I could read too far into things and say she's definitely into me, but in reality she's not. I've made this mistake before, right? And that's what we call a false positive, or technically in statistical terms, we call this a type 1 error, right? A false positive. I think there's something there. I think there's an effect when there actually isn't, right? Or in other words, leaning towards the alternative hypothesis when you actually should have leaned towards the null hypothesis, right? So that's one possible outcome. Or type 2 error is false negative, right? If I'm just kind of down on the dumps about myself, I've also done this one. Then I just say, okay, I guess she's not into me, right? There must not be there. And in reality, she actually is into me, and I just don't move on that. I don't communicate my feelings, so it goes nowhere. That's a bummer, right? That's a false negative or a type 2 error, right? In this case, I lean towards the null when I should have leaned towards the alternative, right? I thought there was nothing there when actually there was something there, right? And so this hopefully helps to depict a little bit more of what we're talking about here. To expand on this table, I wanted to provide you this to expand on this table. I won't spend too long on this other than to say that we've already talked about alpha, our criterion. This essentially, that's the probability for type 1 error, right? In this case, or that's the cutoff, I guess, or criterion for type 1 error. So like 0.05, for example, is right, the cutoff for our tolerance of false positive. And then beta is a different statistic that's representing the probability of false negative. We'll kind of talk about beta a little bit more, or more specifically statistical power a little bit more. But like I said, I don't want to spend too long on this, but I wanted to provide it to you. So I encourage you to go back through the slides and look at this a little bit more closely if you'd like help understanding all of this. And so far, we've answered this key question. Was there an effect? Right? Or in this, my example is hypothetical, so I didn't actually think of a conclusion to that story. We'll say that we'll say it was a true positive, right? That I thought there was something there, and there was. Bam, that's how me and my current partner are together, right? Happy endings, right? So we'll say that was our conclusion. And so we found out there was an effect. We answered this question in step 4. Every time we do hypothesis testing, we're answering this question in step 4. But what we haven't answered yet is a very crucial part of interpreting statistics, and that is how strong the effect is, right? In order to do this, we need to interpret another thing, which is an effect size. So let's talk about that. So I've already used this term effect quite a bit. An effect is any sort of difference or relationship between the sample statistic and the population statistic, as we stated in the null hypothesis, and I guess also in the alternative hypothesis as well. And so we'd say we have an insignificant effect when the null is retained, a significant effect when the null is rejected, right? And so again, that's what step 4 tells us. The effect size is something supplemental or additional to the effect, and that is quite literally what it sounds like. That's the size of an effect in a population. In other words, how far scores have actually shifted in the population. Or even more precisely, it's a percent of variance that can be explained by a given variable. In other words, the percent of variance in one variable that can be explained by another, right? So looking at these variables in tandem. alongside one another. And generally, we should report these when we have significant effects, right? Because I think the real, tragedy, in how we learn statistics in social science, or at least in psychology, is that a lot of people learn to look for p-values, to look for effects, but really don't get any knowledge or training or experience in interpreting the magnitude of that effect, right? A p-value just tells us that something interesting might have occurred, right? But we need to interpret the effect size to really understand the extent, or in other words, or how interesting that effect actually was that might have occurred, right? And so this is a key part that I think is missing from a lot of people's understanding of statistics. And so generally when we measure effect size, or when we look at effect size, one common measure for this is something called Cohens D. And so this is quite literally a measure of the number of standard deviations that an effect has shifted from the population mean in a null hypothesis, right? So it's not a z-score directly, but you can kind of think of it in the same light, I guess, or with the same perspective, right? We're thinking about standard deviations and how far means have shifted, right? And so um, actually, if we go back to that visualization real quick, right? And so again, this is what that's showing, right? The number of standard deviations that this mean has shifted, and therefore you can see here too, we don't need to worry about a lot of this, but percent overlap, that's the part that's shaded in black here, right? The actual percent of the distributions that overlap with one another. So when there is zero effect, right, that means that the means are the same in these distributions, 100% overlap. And then as D increases, we see that overlap decreasing, right? Meaning that there's more variance that is unaccounted for or unexplained by the other variable, right? And so when we talk about variance explained, that's essentially what we mean, right? We're talking about this overlap and how much overlap there is. And so the formula for Cohen's D looks familiar to others that we've seen. M minus mu over sigma, right? So sample mean minus population mean divided by the population standard deviation. So a D of 0 and effect size of 0 means there's no difference, just like we saw in the previous visualization. A negative D means the sample mean has shifted below the population mean. Positive D means it shifted above. And so again, if we go back to this is only looking at positive D. And if we had a negative D, then it would just be moving in the opposite direction, right? If that helps. And overall, the absolute value of D. So in other words, the value regardless of the sign, that increases as the differences get larger, right? So if you'd like to have it all in one slide, here you have it. I guess one thing we haven't covered, some general conventions for interpreting these. These are very loose guidelines, and these guidelines, whenever you talk about guidelines and stats, it's always arbitrary, right? But to have some sort of vocabulary to talk about this with, generally some people say that a D less than 0.2 is a small effect, as you can see here. 0.2 to 0.8, we call that a medium effect, right? So here's an example of 0.5. And then D greater than 0.8, we call generally a large effect. But as you can see, right, there's still a lot of overlap here, right? And so, although we call it a large effect, no, that doesn't mean that it's like these distributions are completely different, right? There's still a majority of variances that's shared or explained by the other variable, and vice versa. And so I won't spend more time on this. You've already seen this, but I do want to mention this here, statistical power. And that is the ability to quite literally to detect effects. Or if we go back here, rejecting the null, right? We're saying that we don't want the null hypothesis. We're looking at the alternative, right? We think the null is incorrect. And when that's a correct decision, a true positive, that is detecting an effect, right? And so the probability of doing that is statistical power, right? The ability to detect effects, and that's absolutely critical in social science research. Or in other words, the probability of detecting an effect or of correctly rejecting the null hypothesis. There's a number of factors that increase power, because again, this is vital. If we're doing research, if we're making all these predictions about things that we expect to see, various effects, various relationships between variables, right? Um, Whatever it may be, we need to be able to do that. So ideally, we use good methods and design in order to increase our statistical power. And so you can see that some of these are kind of impractical, like increasing type 1 error. We don't want to increase error. Ideally, we want to decrease type 2 error, absolutely. Um, Increasing effect size, but some of that's beyond our control, right? If there are really large effects out there, it means that they're going to be slightly easier to find. But generally, the most practical way to increase power is to increase sample size, right? And so whenever people talk about needing to have good sample size, there's a lot of reasons for that, but in a very basic sense, it comes down to statistical power. Increasing sample size is typically the most practical and most beneficial way to increase power. Or in other words, increasing sample size is the most beneficial and practical way to increase the probability that we'll actually detect effects that we expect to occur, assuming that those effects are actually true and do exist. And that's all I got. Thought there was more. This has been a long video. Hopefully it was informative. We'll see you around.